All right, so welcome everybody. Again, this is part 2 of our data lifecycle. Last week we talked about putting in data to ARM, and now we're looking at data review and then the analysis of that data, some commonly asked questions about the report, and then kind of finish up with graphing. So I'll close out of that presentation here. And I've got a short kind of introduction just to kind of set the stage, I think, for kind of this statistical topics that we have. I think it's kind of nice just to give an overview of kind of what we're doing in ARM, and it sets the stage for the tools then that we'll show how to use here in a couple of minutes. So just to kind of talk about the basics, I guess, for what we're doing in ARM. And so, of course, the goal of research typically is to determine if your treatments of interest perform differently. Your choice of treatments could be different products, different formulations, different rates of application, what have you. And we want to know if those treatments can be distinguished from one another, whether it's their effectiveness, safety to the crop, or the cost. Sometimes the hope might be that the performance is indistinguishable if your product is cheaper. So then research trials are performed to obtain observations of treatment performance. In ARM, we'll call them assessment or ratings. But of course, the question is, are those observed differences due to the treatments or just due to random chance? And so that's really where the statistics come into play, namely for us, the analysis of variance. So, you should not just immediately jump into the analysis after you record the data. And we covered these steps last time around. But just to kind of recap, we really tried to separate the steps of looking at your data into a data confirmation, which is really, catching outliers, any issues that occurred with the assessment before we start to consider any analysis. So that data confirmation was what we really talked about last time around. And the importance for that is, if you have an outlier in the data, that can break all 3 assumptions of the AOV, which we'll dive into a little further. But that, an outlier can trigger skewness and make your data set non-normal. The non-additivities, outliers then aren't distributed equally, and a heterogeneity of variance. So all of those kind of trigger points can all really be triggered, I should say, from outliers. So that's kind of one of the reasons we really stressed that step, that data confirmation. And you can avoid some of those troubles by keeping detailed records of the site and the assessment and confirming the data as soon as it's taken. So kind of we called out to some of the data collection options with ARM, and that really helps. And we also kind of looked at the range of values. The minimum and maximum specifically is what we had called it in ARM when you're putting in the data. So we got that all taken care of. Now today's session here, we're starting to think about that analysis of variance. Let's actually look to see what the data is trying to tell us. So, agriculture research it's always subject to variation from a variety of sources. And so we perform an analysis of variance on the data. Statistical variance is a measure of how spread out the data is. We sometimes call it ANOVA or AOV. The analysis of variance dissects the variability in those assessments. So there is controlled variability from the treatments and your blocking structure, and then there's the experimental error, which is uncontrolled. So we're really considering if the observed differences are due to chance, then the variance between treatments must agree with the variance within treatments. So that's really the idea behind the analysis of variance is that thought. Kind of putting it into practice real briefly, just an example output from AOV, just kind of a dummy trial with 5 treatments and 4 replicates. And just to kind of break this up, the degrees of freedom is the first section here on the table. It's a little tricky to define, but it's the number of values in a final calculation that are free to vary. So with variance, your degrees of freedom is n minus 1. So for treatments, you would have 4 degrees of freedom. The sum of squares is the next calculation. That represents the amount of variation in the data. And then it's split up into each source that's listed in our table. The mean square would be the sum of squares divided by the degrees of freedom. So it's really taking the amount of variation and divide it by to the degree at which it can occur. Then we calculate an F ratio, and that indicates the level of variation from that source compared to the random variation. So the larger this ratio is, the more likely that the variance from this source is not due to just random chance. So to quantify that, we calculate a p-value, the probability that the observed differences in the treatment or the block, the probability that the observed differences in the treatment means could have arisen by chance. So a low p-value, typically we say less than 5%, would indicate that we can be confident that there are real differences among treatments. Whereas a high value, like we have between the blocks, that would indicate that there is no evidence of a real difference among blocks in this case. It could be because there is no real difference, or that the differences are too small for us to detect. So to summarize, the AOV analysis breaks apart the variance of observations into different sources. And then we calculate a p-value as the end result. That p-value is a probability. So the AOV p-value is the probability that no differences in treatments exist. So a p-value of 0.04 means that we are 96% confident that there are significant differences between treatments. But we're not done yet, because we need to know which observed differences between the treatments are significant and which are not. So the AOV analysis doesn't give an answer to which observed differences in treatments are significant, just whether there's evidence that there is some significant difference. So the next step is to run a mean comparison test. Sometimes known as a multiple comparison or a mean separation test. These compare the treatment means to determine what differences are significant. In ARM, we have a variety of mean comparison tests to choose from for different situations and research types. The most common ones include LSD, Duncan's, Student Newman-Kuhl's, and Tukey's HSD. So it's usually the next question is, well, which one do I pick? Not really a political discussion, but these tests can be classified by how liberal or conservative they are, meaning if they are more likely to report a false positive, to be a type 1 error, or a false negative, to be the type 2 error. So typically, you can consider the penalty of failure for the study as to kind of which side of the fence you would lean on. If your trial is being used for registration, then a more conservative test would be appropriate. But if you're just doing like a screening trial, it's all about potential. I do have a handout that kind of dives a little more into detail on that if there's any interest as to choosing that option. Don't want to bog us down too much on that, but I do have some information if desired. So let's quickly just run through an example of how a mean comparison test works. The specifics for each test vary a little bit in how things are done, but this gives us just a nice, the basic concept really is the same for each of them. So the first step is to calculate a test statistic to perform on the comparison of means. So in our case, we'll just do LSD, and that LSD value here is 5.49 for this data at least. Then we compare the means using this statistic. So if the two means do not differ by at least that LSD amount, they are not considered significantly different. Then letters are assigned such that the means with no letter in common are significantly different according to the test. So here in this case, we can say there's evidence that treatments 2 and 5 are different because there is no letter in common, but there is no evidence of a difference between treatments 4 and 5, since they both have the letter A. Just a quick warning about this test in particular, the LSD test. It's really intended only for specific comparisons chosen before the data is collected. So when you're using it to make more than one comparison, like across a whole trial that we just calculated here, the true significance level becomes much larger as the number of treatments increase, because there's a lot more pairwise comparisons being made. So sometimes that's by far the most liberal, sometimes almost to a fault. So just to warn kind of about that particular test and how that can end up working, especially the more treatments you have in your study, then the number of comparisons you're performing increases quite quickly, and so that LSD can get pretty extreme as far as the real significance level and that chance of the false positives, the type 1s coming in. All right, so that's the AOV. That's really the analysis that's being performed. We alluded to this earlier, but there's kind of a big caveat to all of that analysis, and that is that the ANOVA has some requirements of the data that's being run through it. And so if those requirements or assumptions are not met, then the results of the analysis can't be trusted. You can't rely upon what we're seeing if the original data doesn't fit those requirements. So to take a closer look at those assumptions, the first one is homogeneity of variance. Really that the variances within the treatments are approximately equal. So if you have a treatment that is much more variable or much less variable than the others, the ANOVA will not work. So to determine if this is the case, we can look at a box whisker graph. We did that last time around and looked at the height of the boxes. to get an idea of the variance, or we can run a test for homogeneity of variance. Levine's is generally the chosen one, but we also have Bartlett's test as an option in ARM2. The next requirement is that the data is normally distributed. So if your data is not bell-shaped, then you can't use the same p-values in the analysis. It's just math is what Peter, our statistician, says. So tests for that include the skewness, kurtosis, and we also have Shapiro-Wilks that we'll see later on. Finally, the last two assumptions are independence of errors and additivity of treatment and block effects. These are a little harder to test, generally are not an issue. Biggest thing really is to not introduce bias in the assessment. Things like edge effects or subjective ratings being influenced, things like that. So the assessment map can be helpful to detect some of those things as well. Like I said, mostly those are kind of built in just to kind of the typical well-rounded way to design the study. If it's done well, the design is done well, typically then we don't have so much concern for those two. So of course, the big question, what happens if these assumptions are not met? So there are data correction transformations, which are designed to correct the underlying distribution of the data without affecting the results. So we've got three main options in ARM. The logarithm, that is great for counts of things that occur in clusters. The square root, that is typically for counts of things that occur at random or rarely would occur. And then the arc sign is used for percentages. There are also spatial models, and those try to recover information about hidden variables across the field. So I think there's 3 trend and 4 nearest neighbor models that can be used in ARM. The caveat with that, it's really, typically you would only do or try one of these models if your blocking design fails. So if we were anticipating a gradient in the field, so we ran our blocks in a particular direction and turns out it was a totally different direction, or things like that, then really can turn to the spatial model, because it essentially is throwing out the blocking entirely. Finally, there's non-parametric statistics, and that actually just throws out AOV and all of its assumptions entirely. And so instead, we're analyzing the data by ranking the assessment values instead. So really, instead of looking at the mean and the variance, you're dealing with these ranks that we can work with, and a median and things like that. Nice thing with that is we still can perform a mean comparison test on the mean of those ranks. So we end up, and we'll see that later on, we can end up using really the same setup. It actually fits real nicely in the very same report, even though it is actually a different different analysis being run instead in that case where you might utilize that. All right, so that's enough talking here without doing anything. So hopefully that kind of provides the basis for what we're going to cover here. We'll show an ARM where we can really run all of that through. So I've got a trial here, and again, we'll really focus on the next step of data review. So really, the next step after we've entered the data, we've kind of confirmed the assessment is the way it should be, and now we're ready to think about the analysis. So as we just showed, we can't just dive into the AOV. We want to look over our data. And really, we're making a second pass through since we've looked at it once when we put it into ARM. Now we're saying, all right, before we analyze, let's review to see if our data fits the assumptions of AOV. And if not, we've got that toolbox we just discussed of a few different items we can use to get it into a place where we can proceed with the analysis. So here I've got a trial. We've got a fair number of assessment columns. We won't go through every single one of them, but they'll provide just a nice set of examples for us. So really, pretty much all of the data review features are kind of nicely compiled for us on the column diagnostics panel. So all the way to the right of your assessment data editor, we had been working on the properties panel last time. That is typically the one visible by default. But if we put that away with the unpin here, there's a column diagnostics. So this one typically wants to be a little wider. So I'm going to pull this over here so we have kind of a comfortable amount of room. And my monitor is just a little squished since I've sharing it, but I think that'll balance it out fairly well. So the column diagnostics panel here, you can see is tied to the selection of what data column your cursor is in. So if I click into column number 2, everything will refresh and recalculate based on the assessment column that you are currently clicked into. So we have a couple of different sections on this panel, and we'll just kind of work our way down here. This top half is the diagnostics table. And so it contains, for lack of a better term, our statistics, or maybe our box score, if you're a sports fan, of information about the data here. So we have, number of assessment values, how many unique values, how many are being included, and then things like if you have any missing, empty, damaged values, things like that. We mentioned those briefly in the data confirmation step as a way to have just a nice overview of what the data looks like to some extent. Then as we get farther down, we get into a little more exciting values here, and we get to see some of our tests for those assumptions of AOV. So we've mentioned previously the Levines for the homogeneity of variance, and then the 3 tests for normality, Shapiro-Wilks, skewness, and kurtosis. So in the table, these values that are being reported for these tests, those are p-values. So really, if that value is significant, that is bad. That would be a sign we have to do something about that particular test. So 0.45 is nowhere near our cutoff of the 5%, so there's no issues with homogeneity of variance. And in fact, they all kind of check out here in this first column. And so this is the raw data, looking just at the data values themselves and running these tests on the data values. That's kind of the results we get. The second column, this IID, this is actually where we want to be basing our decisions on these tests. That is being run on the residuals of the data. Essentially, I like to think of it as really the error that's associated, and is the assumptions are really thinking about those errors behind the scene that we're wanting to analyze, to decide before we go ahead and actually analyze those variances. So really the modern statistical approach would be to use these residuals. If you were taking a stats class 10, 15 years ago, it was probably the methods would be looking at the tests on the raw data, but really the residuals is kind of the more modern approach. And that was kind of one of the big jumps in data review for ARM's sake that was brought about by the column diagnostics in the last few years or so. So in our case, if we look at those four numbers, they're similar in the fact that none of them are significant. So in this case, we can breathe a sigh of relief. Hey, there is no action that we really have to take. There's no assumptions that we are failing, so we get a great green light to go ahead and analyze without any adjustment that we may have to do. So what we can do in that case, we could either just move on to the next column and review, or if we select the IID here at the top, this will add in the ARM action codes that IID code. And in this case, it's really a convenient way to mark that I have reviewed this column. I've looked at the column diagnostics and found that there was no action to take. And just to show IID, it's short for identically and independently distributed. I guess kind of a common phrase in statistics. I had to look it up because I don't remember off the top of my head, but really, again, that's kind of instructions to say, hey, I've looked at this data column and it all checks out. There is no action I've got to take. So that kind of closes the book on that column to say we're good to go. So if I move on to column number 2, you can see that everything is recalculated for us. And if we look, our Levine's value now is significant. So we didn't get quite as lucky with this column. There is an issue with the homogeneity of variance. So we've got that toolbox of things that we can do in ARM, whether it's a data correction, maybe we should do spatial models. The question is, well, what should I do? What will fix it? What would make sense? That's where the recommendations table down below really can come into play. So what the recommendations table does is it takes all 4 of those tests, just like we had up above here, and it will look at the results of those tests and give a recommended action as to what we should do. So in this case, for like the Shapiro-Wilks, skewness, and kurtosis, they all are not significant. There's no problems with the normality assumption. So ARM recommends IID. Nothing you need to do, nothing to see here, carry on. But as we saw in this case, Levine's is problematic. It is significant. We can't trust that all the variances are truly the same. So ARM has the ability to run through all of the different options we have, the different data corrections, the non-parametric statistics and things like that, and see which of those options would be best for us in this case. And so it has found the AL or the log transformation to be the best option. If we look up above here, we have a column for AL, and we can see that it does stabilize the variance. We don't have a significant value there, so that is great. We can control specifically what ARM considers when it's looking through those recommendations. So by default, it just looks at the assessment values, just the numbers we have in this column, and decide what's best. But we can also tell ARM what type of assessment this is. So if we say that the basis is the rating type, then it can look at the rating type, and we know that this is a count. So ARM can then recommend, instead of using the AL, let's do the square root instead. Because as we said, count data is typically better handled with the square root transformation. So now ARM is considering not just the values, but also the type of data we have, and makes a better recommendation that the square root would be best in this case for our count assessment. And it still checks out that the rest of those will all pass, so we feel pretty great about using AS as the code. I could either select it up top here to turn that on for this column, or you can also double click in the recommendations table, and that will then apply that action code. And if you're not familiar with action codes, essentially this is just going to provide instructions to ARM when we go and do the analysis as to a data correction to perform. So you'll notice the values that we typed in have not changed. We haven't changed any of the data. We're simply adding some instructions to ARM for when the analysis is going to take place. All right, we move to the next column. You can kind of get the hang of it. We talked a lot about it, so it seems like it's kind of a slow process, but it actually can be a pretty quick check when you enter a column. Me personally, my eyes gravitate right towards the recommendations table and specifically what code is recommended. And I see in this case, all of them are IID, so I know there's not a single test that failed. So I'll just double click on any one of them and move on to the next column. And depending on the assessment you're doing and how the data comes out, you might have all of them are IID, or maybe some of them need to be reviewed a little closer. Here we've got another one where the Levine's is failing, and so the square root is recommended. There is, if you want to dive in and geek out a little more on the statistics, we do have a graphing functionality here. I'm going to let me do the 2x2, so it'll be a little easier to view. And so for the AS row that I've clicked on here, I can graph. And what this will do is display our diagnostic plots for this data. And on the left-hand side, we have the residuals. So this is without taking any action, what is the data looking like? And so we can really visualize those four assumption tests. So the Levine's, we get to see the box whisker. And again, that box, how you can see treatment 1 is so much more variable than treatment 2, and 4, 5, 6 are all pretty small. So not surprisingly, we can see this p-value here. Maybe I'll zoom in a little bit. P-value here that shows that that's significant. We can't trust that all those variances are the same. There's quite a big difference between them. There's a normal QQ plot that gives you a sense of the normality, and we can see that Shapiro-Wilks test of whether that's significant or not. Similarly for skewness, there's a spread location plot and then a histogram to kind of give that sense of kurtosis. So those are the four plots. If I go back up to the top here, on the left is the data. It's the residuals, but it's the data we're looking at. And then on the right is the recommended code that we had clicked on, the AS. So we can now compare visually, did this make it better? And it does look like it's stabilized. There's still some differences, but it definitely brought those closer together as far as just the size of variance between them. And so that resolves that test. And then we can also make sure that none of these other ones are broken. And no, they still are passing. So they're still acceptably, passing for us. We haven't created another problem by applying a different transformation. So that was the graphs here. You can do that for the recommendations, or up above here, if you're in a particular column, you can also show the graphs from up there. Nice visualization to kind of see your options if you want to dive a little bit farther into the reason for that recommendation. Is it going to do what I want? So I can double click again to say that's the one I want. And then just go on to the next column, IID. And I'm going to skip ahead. I think these all pretty well behave themselves until we get to column 12. So this one for the lodging data here, our Levine's passes at IID, but the Shapiro-Wilks is significant. And if we look at all of our transformations, you'll see none of them ever fix the normality problem that we have. So if those data correction transformations don't resolve the issue, then we can go to a non-parametric statistics. And that is the AR action code, kind of the automatic rank transform. So if we can't fit within our assumptions and our data, the data corrections don't work, like we said before, let's just toss out the whole AOV idea and run a different analysis. And this would be the non-parametric statistics. So I'm just going to double click to add the AR, and we'll see in a moment when we get to the report, it'll actually fit right in with the rest of the columns. But instead of looking at the raw values, we're actually rank the assessment values, and then we're performing an assessment on the ranks. So it's, in general, the AOV has more statistical power. So that's why it's kind of the first option that you typically would do. The non-parametric statistics still are totally viable. They may have a little less power than the AOV, so they don't get to be picked first, but they're a really great backup plan essentially for when the data just doesn't lend itself to AOV. And sometimes that's just going to be the way it is from the get-go. So it's not necessarily, oh, well, we just got unlucky that this particular assessment happened to be that way. It can be that that's just that type of assessment always lends itself to be that way, that it's very hard to get certain assessments, to be bell-shaped. To have normality to them. If you're just counting the occurrence of insects that are, very randomly or sporadic, or there's not a lot of pressure, so there's, some plots have a bunch, but most of them don't, things like that. It's kind of what we have here. There's a whole lot of zeros, and then there's just a couple of plots that have a much larger value. Well, you're never going to end up with a bell-shaped distribution for that. So sometimes that's just the type of assessment that it is. And you can see that too a little bit on the recommendations. If it is that type of assessment, it'll go pretty quickly to that AR. I think that covers really all the different types. Notice we did mention earlier the spatial models. That is turned on or off at the top. So as I said, it's not a every time let's check it out and see what's fitting. You have to be a little more careful when doing that. like I said, it really tosses out your blocking structure entirely, and then tries to not make one up on its own, but look at the spatial layout of the map and the assessment to figure out and try to explain some of that variability that's there. So not, I would say it's almost a not out of the box type of thing that you just want to run with. If you're familiar with them, then by all means, turn them on and look at that. You'll see that when you turn it on, there'll just be some more options. So these are all the possible spatial models that can be considered. There's a few more values in this table to kind of diagnose how appropriate those models may be or not. And then at the very bottom here, you'll see that those get rolled into the recommendations as well. I'll admit I am by no means an expert on them, but it's available if it's something you're aware of, or run it past a statistician to say, do you think this is a time where I should use it before using it necessarily right away. So that is most of the tools here on the diagnostics panel for really reviewing the assessments. Again, just move through all of the columns in the trial to take a look at them one by one. In very rare occasions, you might have a third table on this diagnostics panel, and it would be for outliers. We did this in the data correction section where we showed on the column properties that there was this outliers tool, this outliers calculator. The outliers that are with the diagnostics actually uses a different calculation. I don't know if it has a name necessarily, but it's a lot more conservative as far as finding outliers. We had talked about last time the different options you have on that panel. And so it only comes up if there's a calculated outlier. Otherwise, it remains hidden to kind of save space. And I would say it's pretty rare to see one. I actually had troubles trying to fake one as I prepare the data set and just trying to fake numbers and make a really extreme outlier. And it was hard to do because that was kind of part of the calculation is to be conservative and not just find superfluous outliers, but truly values that are unusual, taking into account the whole data set. But if you're curious, it does rely on the maximum standard residual, I believe is what that stands for. And if there's 3.4, if the column has higher than 3.4, that would be kind of the trigger for being an outlier. So finally, last button here I should not ignore. We do have the capability to take all of this analysis that we've looked at on the diagnostics and actually send that to R. So that's what we're using in the background to perform this analysis. And so ARM is using R. If you also use R, we can share our code essentially with you. So this will generate, whether you're using the R Studio or the more command line R, it will create the script that was used to generate this information and just save it to an R file that you could open. You can see what we're doing. You could take what we're doing and do some more things with it, whatever you want. It's a nice way to share that information. And then we have kind of the comparable code that could be used in SAS. So if you're using that as well, that's an option for just taking what we see here on the diagnostics here and being able to use that for your own good. So Then the last main thing to mention with the data review, if this all kind of sounds foreign, I've been using ARM for years and years. I've never had to do this because when I print my report, ARM asks me about assumptions. That is in the print reports. It's definitely not something you made up. It has been there, but I would encourage you to turn that option off, and we'll show you where that is at. So in your AOV means table report options, we're actually looking at the general summary tab, and towards the bottom here, probably one of the longest options in ARM, apply automatic transformations or treatment exclusions to data columns that violate assumptions of AOV. So that's a long one. That really kind of describes what we were doing manually in the column diagnostics. And so historically, this was set to prompt. So when you generate the report, ARM would look through all of the columns and make some recommendations. The trick and the reason why I would recommend changing this from prompt to no is that that engine, if you will, that all of that logic that's testing for the assumptions of AOV, that was using that raw data column. So that was using the 20, 25 years ago statistics approach. And that's really when that was added. Now we've got a new approach just statistically in the industry. And so we have a new tool for that as well. So that would be my soapbox recommendation. Turn that off and kind of bring the more modern statistical approach of going through each column with the column diagnostics. And you're looking at, the calculations will be different. And then a lot of times you actually see a difference in the recommendations because the results of the tests on the raw data may differ from the tests on the residuals. And just industry-wide and in statistics in general, that's just kind of the modern way to do it, is those residuals. So again, that was on the general summary. It's nice. Some people say, yeah, but it's so nice that ARM just does that all for me all at once. And yeah, that is very convenient, but I think being able to look and make that choice, it's usually a pretty quick choice. We talked through it, so it took a little while, but I think that's important to look at each column, or at least the columns that matter the most. That moisture content column, well, we don't care. We're not looking for statistical differences in the moisture content when that really only pertains to the yield. So you don't have to do every assessment, but the ones that you're going to statistically analyze would be the focus for the review. All right, so that's really the data review step. We've wanted to make sure that the data is ready to be analyzed. So now we're ready to the exciting part of actually, let's actually do the analysis. So if you haven't done this before, in our print reports, really the main, the flagship report, I would say, of ARM, most likely would be this AOV means table report. And there's 1.5 million options here that we can look at. I'm just going to take the defaults for the moment just to talk through what the report gives us, but then we'll be back quickly to cover some of the common questions, I guess, that sometimes trip people up. I'm just going to take the defaults here as I generate. I just kind of want to generate the report and just real quickly introduce what that looks like to anyone who has not done this before. All right, so previewing the report, we're going to basically have the assessments as really the heart of the report. We zoom in a little bit. So each assessment column that was performed is going to be in the middle of the page with the header details that we want to include to describe the assessment. Then we have summarized for each treatment, we have the treatment mean across those replicates. Then we have performed that AOV analysis. So we get the statistics down below here and the results of that AOV. And then as we talked about, if the AOV says so, we should now proceed to perform a mean comparison test. And so we get the letters to the right to tell us which treatment, which treatments are significantly different than the other ones for each of these assessment columns. And then I guess I have just the brief AOV table. If you prefer to see all of the sources of variation and all of that AOV table like we did in the PowerPoint, there's an option. Instead of doing just this really brief table, you can see the full thing and really dive into all the statistics there. But you can see kind of what we achieved earlier with the action codes. For some of these, we have our square root transformations that were applied. And so what happened was ARM took that raw data from column 2 and then performed a square root transformation on all of the data points and then performed the AOV analysis on that data. So that's really the statistics here are all tied to that information. And then the D in the DAS is telling us ARM then de-transformed the data back into the original units, because I can't really think of what the square root of a count would mean. So we bring that back into the original units again to make a little more sense on the report. And then I'm just going to keep going over to find that column 12. That was our automatic rank, so our non-parametric statistics. And so again, as we showed, it's actually pretty nice because although we didn't perform the AOV analysis, we're still able to fit it onto the report here. You can see there's no standard deviation or grand mean reported because those are irrelevant to the non-parametric statistics. And instead we generated ranks, and that's what that R means there. So what's displayed would be, I think since we're de-transforming, those are actually the treatment means, but all of the analysis and the mean comparisons that were performed was done on the ranked data, doing that non-parametric statistics. So that's the AOV report. I'm going to close this trial. And I've got a trial kind of mocked up for the most common questions that we get for reporting. I think that is maybe the best way to really cover the tricks with working with the report. So the most common one, and most common we get for questions is, where are my letters? So that usually ends up being the question of the whole season. Really, we can just tell as soon as data starts coming in, because then our sport box has a bunch of reports and PDFs and saying I'm confused as to what ARM is giving me. So let me preview this report here. And so there's usually kind of a few possibilities as to where are my letters. This first one, column number 1, we'll see I've got these weird negative signs. I don't have any letters. There's just a dash instead, where I would be expecting to see a letter. And so that is showing that there's no significance found in this column. And there's an option So if I go to my report options, in this first section for the mean comparison test, you can define what symbol you want to use when there's no significant difference between treatment means. And by default, we use the dash, but some people may prefer like an NS for no significance. Some may prefer just letter A, so that then the whole column, if I preview here, then the whole column has just A's all the way down to show that there's no significant differences. So depending on what you'd want to denote for when there's no significance, you can enter that into that text box there, and that's what ARIM will use. And so by default, we just have that dash, but you can certainly change that in your options. Another question, maybe they know that option, but the concern is that I would expect to have differences. So for whatever case, I'm looking at my list of numbers, and while I very well think that there should be a difference, or many times they'll reference the LSD value and say, well, I used that, and looking at, I'm not sure if in this case we have a big enough difference, the 12.5 to the 11.6, I guess column 1 doesn't quite do that for us, but they'll say, according to the LSD, treatment 5 and treatment 2 should be different, and yet the report doesn't show that. So how come I'm not getting my letters? Most commonly, the reason for that is if you look at the treatment probability of F, that's that p-value we were talking about earlier at the kind of the end result of the AOV analysis. In this case, it's a 0.6094, so very much not significant. So the AOV analysis did not detect that there were any differences in any of the means. So if the AOV doesn't see any, then what would be the point of running a mean comparison test to find out which differences are significant when we didn't find any differences in the first place? Is essentially the idea behind that. So even though maybe the LSD could try to detect a difference that's significant, if the AOV doesn't in the first place, find any differences, then we shouldn't even be running a mean comparison test. So that's the logic behind that behavior. It can be controlled by an option. So back on the report options, the only when significant AOV treatment P of F, that is on by default, and that performs what is called a protected test that we just described. If AOV can't find it, no point in looking any further to run a mean comparison test. And so ARIM will just report no significance in those columns. If you have a reason to not follow that and you want that mean comparison test run anyway, you can turn that off. I'm not sure, statistically might not be the recommended thing, but again, that just depends on the situation. One more common question, looking at my data, column 5 here. I'm looking at my numbers, and for some reason, I don't have any letters next to a particular treatment. Why is that blank? It definitely should be significantly different than the rest of these, but it doesn't even have a letter. The reason for that would be, if you look in the action codes field, that's kind of the next best place to look to try to understand what's being done in the analysis. And in this case, there's an ET1, which means exclude treatment number 1. We could have also maybe had the EC, which excludes the check treatment. So when you're doing some of the assessment review, we go to column 5 here, there are a variety of action codes that will exclude certain pieces of information, certain plots, or in this case, it's a treatment. If you want to exclude the check, I think in this case, it was pretty clear the check was different than the rest of the treatments. And so in some cases, we shouldn't even be counting the check. We really are more interested in the statistical differences between our treatments. And so you can exclude whether it's a check, whichever check treatments are in settings, or you can call out a specific treatment number. You can even toss out an entire replicate if you need to. ES will actually hide that whole data column from your report. So it'll simply not ever show up in the AOV means table report at all. Similarly, you could turn it off for ST so it doesn't show up, or you can tell ARM to not analyze the data. Some of these just depending on the options of what it should report on the report. That excluding a treatment, there's another way to do that. So that's kind of a common question too, is I need to throw out a treatment or I need to throw out a replicate. How do I do that? Column by column, if you have a specific assessment where that needs to happen, you would use the action code. But in the print reports, you can actually toss out a treatment across the whole report. If you go to the global report settings, you can choose to print selected treatments. And then ARM will ask us when we go to generate the report, which treatments should be included on this report. And so that'll cover all of the assessments that are on the report. Similarly, if you go to the general summary, we can do the same thing for the assessment data columns. Automatic will include any column that has data, but I could certainly do a select to choose which columns to have on my report. That's kind of a slick way to actually change the order of the columns if you want. Same thing for the header rows. So when I previewed the report earlier, ARM was asking me which header rows should I have. So I can choose to select the components I would want. And down here at the very bottom, if you need to drop an entire replicate in all of the assessment columns that you're having on the report, that is at the very bottom here, print selected replicates. Again, same thing as those other ones. It'll ask you which replicates to include. So then you can say 1 through 3 if the 4th replicate needs to be dropped or whatever. Just a couple more quick hitters. Number of decimals for your accuracy, especially if you have a lot of calculated columns or things like that. You can force the number of decimals of accuracy for all of the columns with this option here. Otherwise, in the header, there is on the very last row, I think, of the header, there's number of decimals. So you can choose for a specific assessment column how many decimal values should be displayed and where ARM should round to. Again, that's really helpful for calculated columns where you just end up with tons of digits and there's no need for that. If you have a long report, that's probably the last kind of common question we see, where the table falls onto another page. I have this, my last treatment ends up on a different page and I can't get it all to condense down. Typically the best thing, the best way to kind of cut down on that would be to shorten this header section. You can see here in my case, I've just got a lot of rows and maybe not all of them are the most important for my final reporting. So, maybe I don't need all of these intervals or, maybe I can get away with just my crop code and I don't need the scientific name, or whatever you'd want to cut off of there. That can be handy. Again, just that general summary, being able to select the assessment header rows, kind of just trim down how many you choose. That can really shorten the length of the report and start to fit things nicely on a page instead. All right, so that wraps up the reporting questions that I wanted to cover. Final topic then would be to show some of the graphing capabilities in ARM. I'm just switching to another trial that, again, is just kind of doctored up a little bit for graphing. Got a couple of assessment columns here again in this trial. So if we want to work on graphing, that kind of has its own section. So it's not in the print reports area, although some reports might have some graphs included with them, but by and large, it's mostly just kind of text-based reporting. Wanting to kind of visualize and graph the data, instead, we have kind of its own graphing tool here. So if I create a new graph, there's a short little wizard to kind of set up the report, choosing which treatment numbers we want to include. You can pick and choose which ones you would want. If you are going to take all of them, you don't even have to click anything. If you leave the box blank and say OK, that'll grab all of the treatments for you. Then we can choose which assessment columns we want to graph. I'll just graph the first one to start with. Then when we go to make the graph, the labels for the axis, we can choose kind of what's important to us from the assessment to describe what we're graphing. So that's asking us what labels here. So you can choose which assessment fields that ARM can grab the information from. So I'll stick with the default of pest code in this case. Then we have our graph options. So I think I'm first just going to take whatever options we ended up having on here, and I'm going to say OK to get into our graph window. We had saw this last time with the box whisker. So that was great for data review. If I go back to my options, kind of a nice way to slowly tweak your graph the way you want is this options dialog will pop up in front of the graph. So you can make a change. I'll change the graph type to a bar graph. And if I hit apply now, that will refresh the graph behind there. So as you're wanting to tweak and see what change might impact the graph in what way, it's a real nice way to be able to keep toggling back and forth. And I can go, wait a minute, that doesn't make any sense. I would rather see it grouped by data column instead, which in this case, I've only got one data column, so that's not going to make a whole lot of sense. But you can change the options and see kind of the immediate impact that will have on the graph. So I guess maybe we'll kind of run through real quick the options here we have. Overall, you really have some control over pretty much every component on the graph to change and tweak to get the way you would want. So graph type, we saw that there's a bar graph. You can also generate a line graph and a box whisker. Maybe I'll stick with the bar graph to start with here. You can change the orientation and how things are grouped. Maybe you want them stacked up instead as a percentage or whatever. Kind of depends on what data you have selected. whether it would make much sense or not. So that's just going to set up the overall construct of the graph. On the fonts, that is the text in the different titles and labels and legend that we have here. So you can control what font is used, any styling it has, and also the size. The font size would be included in that selection of the font. And that you can just choose which component you want to edit and then change the information about it. The labels, that is for the x-axis. Right now I have them showing as a legend, which works pretty nice. If I turn that off, you'll see why. So we're drawing different treatment information that matters to us. And then just depending on how much information you have, you kind of start to lose the space you want for the graph. So that x-axis labels as legend. It's even on the main graph window in the corner because it's a popular recommended option just to make things a little smoother, easier to read. But this is treatment information. It's really being pulled from your trial map treatment description. But we can rebuild that. And so if we reselect, it can ask which fields from the treatment editor do you care about that I can then build up this description. Or you can always hand type too if you needed to. Maybe I don't care about that second component there or whatever you'd want to tweak. You can always hand edit. And if I do change that, it is going to ask if I want to also update my trial map where that description came from. And I'll say, sure, let's do that. You can also turn on or off the AOV mean comparison letters. Now, those come directly from the report. So your report options that you have chosen will directly impact those letters. Data labels, so that will show the specific value there next to whatever point is being plotted. Legends, that in this case, since I've got the x-axis, let me turn off the x-axis labels as a legend, so that way we would have just the one. And so this is going to be the colors associated with each treatment. So if I wanted to change the color selection, maybe I want to do this turquoise, and maybe that's probably too close then to that color. So I'll just pick a different, maybe I'll just run down the list here since they all kind of work together. That'll change the colors there for your treatments there in this case. Again, depending on the graphs, the assignment of what that means might be different if you were graphing multiple assessment columns or something like that. Here we can control the title, so the actual text on these title sections. This was pulled from the header section, but you can hand change it. Left title, right title, neither of them are displayed at the moment, but I can display those to label your axes if you'd want. That was part of the choice we had made when we first entered here, selecting the assessment header fields. What does that look like? And here maybe we want that rating type and rating unit, because that most clearly explains the graph and what was assessed. Axis options will allow you to control what gets drawn, at what scale it might be drawn to. Do you want grids? Do you not? Again, really pretty much, any component of that graph, there's a spot for it that you can kind of control or tweak if you need to. Probably the most common one would be this y-axis scale. Zero origin is really nice because, of course, it shows 0 at the bottom, and then it'll just auto adjust based on the data. But if you did have a specific desire that I only want to show, between 10 to 100, you can do that and control how many ticks. In this case, there probably should be 9 of them, gives us the nice even number. So you can manually override the scale if you need to. But that zero origin works best if you're going in between assessment columns, because it'll auto calculate and adjust based on the data that's there. Colors, really, again, kind of like in the fonts, you just pick what you're looking at, graph title, and then you can choose the color. The foreground color is typically the text itself. So if I wanted a bright red for some reason, I could do that. And then the background color, of course, is that box behind there, which maybe if I don't want the box at all, might work good to make that white. And I can get rid of that drop shadow then if I want to totally really hide that box because I don't like that at all. That's a nice way to really make it disappear entirely. If you want to draw error bars, those are here. So if you wanted, most commonly it seems to be, I want to have my standard error displayed, then you can turn those on, but there's various other values you can include as well. So those are all the various options for configuring the graph the way you would want. When you're looking at a graph, this was data column number 1. Pretty easy to generate a similar graph for your next assessment. So this moves me to data column number 2, which is just a column of 0. So that's not terribly exciting. But if I move to column 3, then I get to graph the data from that column. And here, that y-axis, you can see it changed. It's still at 0, but now it changed to 35, just to fit nicely whatever the data is there. So that works really good. Just if you want to move through a bunch of columns and generate graphs pretty quickly, that's kind of the easiest way there. And so to use the graph, what's the best way to kind of save this graph and utilize it somewhere? There's a few options. Kind of the easiest and quickest would be the clipboard button. There's a button down here for clipboard. Also in the upper corner, this 2 little pages is that very same clipboard button. And that basically takes a screenshot, more or less, of the graph as you see it, dimensions and all. So then you could drop it in a PowerPoint presentation, throw it in an email. Here I'm just opening Word and doing a paste just to visualize it. And if I zoom out, try to fit it here on the page. Again, that really just takes the picture. So depending on the size that you've dragged your graph, kind of has a role in it too. So if mine's really narrow for whatever reason, when I hit copy, you'll see the very same, those same dimensions that when I paste, play it roll. So if find your biggest monitor, if you want to have a really big graphic or whatever, that the biggest monitor you can find when you're working on the graph can give you the largest scale graph essentially when you're sending that to the clipboard. Although, and once you've pasted it, you'll notice that this is just an image. I can't change anything now. Once it's in a different program, it's just a flat image. But if I did want to change something, of course, I could just come to ARM and make the change and then hit copy again and replace that image. There's a couple of save options as well. So when you're on the graph dialog here, we have a button to save. So that would save this graph as a GRF8. So that is specific to ARM. So another program wouldn't be able to read it. it really saves this graph file kind of specific to this trial. So if I'm going to come back to this trial and want to kind of pick up right where I left off with the graph settings and how this looks, specific to this trial, this GRF8 would be handy for that. I haven't done that very much. I feel that the options here, if I'm in the graph options, you can save a set. So that's just subtly different, just a slight difference. It is GDF8, so the extension is different. And really what you're saving is just like a report set, where it's really saving the selection of options that you've configured. We're saving that as a file that can be loaded again when I'm in a different trial, a different scenario, want to create a graph and want to have the graph be very similar to the last trial, essentially. That's really saving your options, saving all the settings you chose to create a graph is what you're saving if you're using a graph set. So for me personally, I'm not doing a whole lot of data processing. I'm just training on it, but at least in my mind, that just makes more sense to me of saving the options. And maybe that's just because we do that in a lot of other areas of ARM too. But that's the difference between those two. Just depending on what it is you really want to save. Again, those are specific to ARM of reloading and remembering what was used to create this graph. Finally, if there wasn't enough save options, there's one more. Save as here on this graph is going to save this graph image as a particular image type. So kind of like when we did with the clipboard, where we saved that image to paste it into Word or wherever. In this case, we're taking that screenshot of this image, but saving it to a file. So these are all different file formats. And then you can specify where should I put that. So here it looks like it's just going to drop it onto my desktop, which is just fine. And then I can, sorry, it's on my other window here. But now it's just a JPEG file right on my desktop. And again, it does not have anything I can edit anymore. It's just a flat image that I could then, again, load into a PowerPoint or send in an email or whatever you may want to use it for. So that's the basics of graphing. I do have just one scenario I could run through quick to show a multi-column graph. But just looking at the time, I did want to make sure I left a little time for questions too. So I'll open the door for questions on any of the things we've covered so far. And if there are none, I can show that multi-column graphing example real briefly as well. But as typical fashion, I get long-winded and don't want to leave out any chance for questions. Cover kind of a wide range today, I think. Hopefully, at least it's adding tools to the toolbox, or the memory of a tool. So when you do get to the data analysis time, you go, what was that? And then you can send us an email and we can remind you what the tool was, or you can check out the recording to refresh your memory. It was one of the challenges for these webinars. Let's cover the whole year, knowing that there's 0% chance that everyone is in all of those sections of ARM at this point in time. All right, well, Not seeing any other questions. I guess I'll quickly do the multi-column example. Actually, I didn't want to close my graph. One real quick shortcut, whenever I just really want to get to a graph fast, if you use the box whisker button on the properties panel, that'll just get you to the graph right away instead of stepping through all those options. So that's one little trick. But there is a Reselect Data button here. So if you have gotten to that point, but then you want to start over with that selection process of what to grab, Reselect Data will do that. So what treatments do I want? We'll bring all of the treatments with. Now I don't have a whole lot of assessment columns to include, but I'll choose 1 and 3 this time. And it's valid in this case, I'd say, because they both are stand counts just done a week apart. And when we choose more than one column, ARM is just going to have us confirm, okay, what's your intent here? Are you trying to create one graph that has 2 assessment columns on it? Or were you kind of picking which columns you plan to graph and you want to still graph one at a time? And that would be the no. So in this case, I'm going to say, yes, I want to create one graph that has both of those data sets in them. So I will say yes, and we'll take the header description. Yes, in this case, the rating type isn't going to tell us anything, so I'm going to include the rating date because that matters to us as well. Oh, and I had the box whisker graph selected, so I want to do a bar graph instead. Let's see if that worked for us. It did. All right. So now what I have is really 2 data sets. I've got that column 1 in the blue and the column 3 in the red. So I have more than one data column, and some of these I turn the error bar off and maybe even the labels, but just to clean this up a little bit. And the x-axis as a legend would be good as well to move those out of the way. But just to show that it is possible to incorporate one or more than one assessment column in a graph. So for the bar graph, it's kind of nice just to see them side by side, how they stack up against each other. You could do a line graph, but instead of having it with the treatments, you could kind of transpose it, if you will, and group by data column instead. So now we end up, let me turn off my other legend so we can see the one here. So we have date 1 where the treatment was at, and then date 2 where the treatments were at, to kind of give you that time flow. So that's another way to do that, which would segue into, if you've used the AUDPC before, that'll also create kind of a time series like that. But that was the key. Just reselect data and choose more than one column, and you can have even more options for the graphing. All right, well, that was all that I had for today. We've kind of capped out on the time as well. I appreciate you all joining us today and the series in general. Hopefully there was some things you were able to pick up and learn on. If not, luckily next week we've got the Q&A session, so feel free to join us if you have any questions, whether it's a tiny specific little question on one little thing I mentioned or you want to know about, or if it's a big broad general, I want to know how to graph weather data, or something like that. We can do big and small rocks, however you feel. So until then, thanks everyone for joining us.
Thanks, Matt.
Yep, thanks. Have a good, I guess it's a good day for you guys. You're closer to the weekend than we are. So